I'd like to welcome you today to the David Bradford Seminar Series hosted by the Center for Policy Research on Energy and Environment at Princeton University in the School of Public and International Affairs. I'm Denise Mausral, a professor joint between C-PREE in the School of Public and International Affairs and the Civil and Environmental Engineering Department at Princeton. Today, it's my pleasure to introduce Dr. Yueming Q, also known as Lucy Q, who is an associate professor in the School of Public Policy at the University of Maryland, College Park. Her research focuses on using big data with quasi-experimental and experimental methods to answer empirical questions related to the interactions among consumer behavior, energy technologies, and incentives. Her research projects have been funded by the National Science Foundation, the Sloan Foundation, the Department of Defense, and the Water Research Foundation. Dr. Q received her PhD at Stanford University from the Energy Economics program in the Civil and Environmental Engineering Department, and her Bachelor of Science from Tsinghua University in Environmental Engineering in China. She's published in top scientific journals, including Nature Energy, Nature Sustainability, Nature Communications, and the Journal of Environmental Economics and Management. Today, her talk will be on applications of big data on residential properties to provide decision support for decarbonization policies. Lucy, take it away.
Yes, great. Thanks, Denise, for the nice introduction. And thanks, everyone, for coming to my talk. And again, many thanks for the center for inviting me to share my research. So let me now share my screen. All right, so let me start. All right, as Denise mentioned, I'm going to talk about some research that we have been doing that combine real estate data with energy data to provide decision support for energy and decarbonization policies. So in today's talk, I'm going to talk about three separate projects that utilize such data. For the first project, we estimate empirically the policy incentives on energy technology adoption. And the reason we're doing this is because of the energy efficiency gap that the economists have observed in the diffusion of energy efficiency technologies. So what this concept means is that despite the fact that energy efficiency technologies can provide positive economic benefits, and also despite that there are various types of government incentives provided for incentivizing the adoption, the diffusion of this technology is still relatively slow. So as a result, we want to provide empirical evidence about the exact impact of various types of policy incentives on technology adoption. Right. And then in the second and third paper, we are basically providing empirical evidence about the impact of technology adoption and the impact of natural gas leakage on housing prices. And the reason we're doing these two papers are because these the answers to these questions can help policymakers to evaluate the costs and benefits of technologies and interventions in the energy system. Okay. And the funding for this research is provided by the Sloan Foundation. Okay, so that's the overview of today's talk. So let's now move on to the first project, where we analyze the effect of rebate and loan incentives on residential heat pump adoption using evidence from North Carolina. And this is joint work with my current PhD student, Xin Shen, and Dr. Pengfei Liu from the Ag Econ Department at University of Rhode Island, and my colleague Anand Patwardhan from my department. And also want to mention that this first paper is still a work in progress, so your comments and suggestions will be very helpful while we're preparing the submission of this paper. Okay, so a little bit background about heat pump and why we're focusing on this technology. So this technology is actually quite important for building electrification. So I know this is not a physics class, so I will just quickly summarize how a heat pump works. It basically extracts heat from sources like air, water, or ground and transfer it into homes during winter. And this process can be reversed to cool the house in the summer. And the heat pump itself is powered by electricity, but the important role of heat pump is that it can free up the furnaces from burning natural gas. So, and because we know that natural gas still emits carbon dioxide and other environmental pollution. So if we can basically electrify the natural gas burning furnaces while also cleaning up the electricity grid by using more renewable energy, then that can facilitate the economy to reach deeper decarbonization. Right, so some policy backgrounds, as you probably already see from the news headlines these days. Building electrification basically has gained a lot of attention from the policymakers. For example, from the current administration's climate change plan, they plan to provide direct funding through cash rebates and low-cost financing to upgrade and electrify home appliances. And also, last month, California passes the nation's first building code that established the pollution-free electric heat pumps as baseline technology to facilitate the transition to building electrification. And also, not just California and the US, there are also governments worldwide that have adopted various types of policy tools to incentivize or facilitate the diffusion of heat pump technology. And because of this various type of policy incentives, what we're interested is exactly empirically what are the impact of rebate and low interest programs, which are the two most widely adopted incentives for this type of technology. And as I mentioned earlier, the reason this question is important is because of the existence of the energy efficiency gap. Okay, and the answer to this question can help policymakers to more accurately evaluate the effectiveness of these policy tools, and as a result, to design more effective policies. And then this paper is also related to ongoing literature that evaluate the policy effects on various other type of residential energy technology, such as solar panels, energy efficiency appliances, and electric vehicles. And another contribution of this paper is that we also make a comparison between the effectiveness of rebate versus loan policies. All right, so given the title of today's talk is on data, so now let me spend some time to introduce the core data set we're using for all three papers. So the data is basically the individual property level data set that we obtained from Zillow through their Z-Tracks program. And then from this program, in total, we obtained 4 terabytes of data for more than 150 million homes in 51 states. And there are 2 parts of the data set. The first one is the assessment data, which records for each individual building the building characteristics, such as the number of rooms, building square footage, year built, and so on. More importantly, also record for each individual building the type of heating and cooling technology. And this include, for example, the natural gas burning furnaces and heat pump and other technologies. And in addition, we also obtain the property level address and prior assessor valuations. And the assessment data was not just conducted once. As you can see from this timeline here, the assessment data were actually conducted or recorded about every 6 months each. The first one was conducted or recorded in March 2016. And then subsequently, we obtained the updated assessment data about every 6 months. Okay. And then this different and repeated assessment data is important because building characteristics can change in the subsequent assessment data. And then, for example, let's say that in March 2016, for one particular building, it only had natural gas burning furnace as the main heating technology. And then in February 2017, in the new assessment data, that building now had a heat pump installed at the house. Then we can infer that the timing of heat pump installation will be between March 2016 and February 2017. Okay, and then that timing is quite important for us to form a panel data set in order for us to do various type of econometric analysis. All right, so in total for the assessment data, we obtained the information for individual property for about 200 million parcels in over 3,000 counties. And then the second part of the Zillow data is the transaction data. Basically for each house, for every historical transaction sale, we can record the transaction prices. And this again gave us more than 374 million detailed public transaction records. All right, so as I mentioned earlier, from the assessment data, we can infer the timing of heat pump adoption of each individual building. And here we plot the heat pump adoption status at county level, meaning that we're plotting the county level density of heat pump in 2020. So here you can see that the adoption of heat pump is not even. There's a lot of heterogeneity, regional heterogeneity. And the region that has the highest density of heat pump are for example, Washington State, as well as North Carolina and the other southwest region of the US. All right, and then using the 2020 assessment data, we conduct a very simple cross-sectional analysis to look at what are the factors that can help explain the regional heterogeneity of the density. So here are the results of that simple cross-sectional regression. Here, x-axis shows the different factors and y-axis shows the impact of each factor. Here, this vertical orange bar shows the 95% confidence interval. So here you can see the factors that are most correlated with heat pump adoption include income, electricity price, natural gas price, cooling degree days, and heating degree days. And the fact that electricity price plays a very important role implies that consumers are indeed looking at the economic benefits and costs of adopting heat pump. And that implies that price-based policy incentives can potentially influence the adoption density because consumers are indeed evaluating the cost and benefit of adopting heat pumps. All right, so this provides some descriptive evidence. And next, we're going to look at the causal impact of policy incentives on the adoption. And here we're focusing on North Carolina because of its relatively high density of heat pump adoption. And now the rebate amount in North Carolina for an average heat pump system range from $200 to $500 per system per installation. And then utilities in North Carolina also offer low interest loan program to incentivize the adoption of heat pump. And the interest rate in this loan program range from 4% to 9%. And these are considered as low interest or as an economic benefit because the average personal loan interest rate and then the credit card interest rate from commercial banks available to consumers are about 10% and 15%. So higher than this interest rate they can obtain from the low interest loan program for heat pumps. And then for these loan programs, the maximum amount of money that can be borrowed range from $5,000 to $10,000, which is high enough to cover the average price of heat pump installation. And then the loan repayment period, the average payment period is about 60 months. Okay, so as I mentioned, we're interested in the causal impact of rebate and loan interest on the adoption of heat pump. And also because of the timing of the heat pumps that we can infer from the Zillow data set, that panel data set enables us to do a difference in difference analysis in conjunction with regression discontinuity design. So I know that we only have 45 minutes, so I will not go into the detail of the regression models. But if you're interested in the difference in difference analysis or the regression discontinuity design, feel free to ask me during the Q&A. So the key idea is that we're selecting 3 regions in North Carolina where there are 2 utilities whose borderline of the 2 utilities lie within the same city of that region. So for example, let's look at this first selected region where we're looking at the borderline between Duke Energy and Rutherford Energy. Okay, and then so Duke Energy started the rebate program for heat pump installation in the second period of our study sample, but Rutherford in our study region or in our study sample did not have any incentive for heat pump adoption. Okay, and then second, most importantly, that the borderline between these 2 utilities are not the same as the city borderline or the county borderline. So these borderline lie within the same city or within the same zip code so that we can ensure that there will be no other city level confounding factors such as city level policies or city level marketing campaign that can influence the adoption of heat pump. Okay, and in our main analysis, we further restrain the comparison to be just within 3 miles to the boundary. For example, we're comparing households located in Rutherford utility and also located within 3 miles to the boundary with the Duke Energy, with the households located within the Duke Energy utility service territory, but also located within 3 miles to the boundary. So this way we can further ensure that we're comparing apples to apples. And the only difference is that one utility offers incentive for heat pump adoption, but the other utility do not offer that incentive. Okay. All right, so to summarize, we have in total 3 such selected regions. For example, the first region I already discussed is looking at the impact of rebate is between Duke Energy and Rutherford. And then second region is between Duke Energy and Union Power. And the third region is between Duke Energy and Haywood Utility. Okay, so to summarize, in the first case study, basically Duke Energy started the rebate program in time period 2 in our analysis, but Rutherford had no incentive at all in both periods. Okay, and then because of this, we can first calculate the difference of heat pump adoption between 2 time periods in Duke Energy as well as in Rutherford Energy separately. And then we subtract these 2 differences, and that gave us the difference in difference estimation of the impact of rebate on heat pump adoption. And then in the second and the third case study, Duke Energy always had rebate program in our analysis. And then the difference is that the other utility had low interest loan program in the 2 time periods. And then we're looking at the relative effect of rebate over low interest loan program in these last 2 case studies. All right, so now let's look at the main results. Again, I will not go into the detail of the two-way fixed effects model, but if you're interested, we can discuss more in the Q&A session. All right, so now let's focus on the coefficients that's within this green box here, and that's the coefficient for the rebate policy. And here we have various different model specification with different control variables. And you can see across all different model specifications, that coefficient is positive and statistically significant. And based on these coefficients, if a region has a rebate on the magnitude of $300 to $500 per system, then that can increase the probability of individual households to adopt heat pump by about 2 to 5 percentage points. Okay, and then considering the average current heat pump density, and that 2 to 5 percentage point increase is equal to about 26% to 28% average increase in adoption. Okay, so it's a quite a large effect, policy effects on the adoption probability. All right, so and the next, I also present the graphical evidence from the spatial regression discontinuity design. Here, I show you 2 figures here. The left-hand side, we use the polynomial feed in the regression discontinuity model, and then the second use the local linear feed. Here, this vertical line basically is indicating the borderline between Duke Energy on the right-hand side and then Rutherford utility on the left-hand side. And the y-axis, you can think of it as the adoption probability. So here you can see that at the borderline, there is a sharp jump in the probability of adopting heat pumps. So this gives us another strong evidence of the positive impact of rebate on the adoption. Okay, so that's the first study analyzing impact of rebate. And then the next 2 study region, we're analyzing the relative effect of rebate or the growth trend of the heat pump adoption resulted from rebate versus from the low interest loan program. All right, so now let's again only focus on the coefficients in this green box. Here you can see that that's the coefficient for Duke Energy, which offer rebate. You can see those coefficients are positive and statistically significant, implying that compared to the low interest loan program, rebate policy is more effective at increasing the adoption probability. So there could be 3 potential explanations for why rebate is more effective. The first one is that the credit constraints can actually be small in the developed region like US. For example, people can easily have access to their credit card loan so that they have low credit constraint. And as a result, the main advantage of loan program, which is to fill up the liquidity constraint, is no longer very obvious in the developed region. Okay. And the second reason could be because consumers may be inattentive to the subsidies caused by the low interest program. And this is because of their cognitive constraint or the constraint of their time. For example, in order to actually quantify the benefits provided by the low interest loan program, they need to understand the formula used to calculate those cash flow and then calculate what's the equivalent financial benefit provided by those low interest program. And because of the cognitive constraint, some consumers might be inattentive to the financial benefits provided by the low interest program. And then lastly, another potential reason is that the consumer's actual perceived discount rate might be low. So despite the fact that I showed you earlier, the average personal loan interest can be higher than these 5% or 9% low interest loan program, but then the consumer's actual perception of those discount rate could be low. Okay. All right, and then we also conducted a bunch of robustness check. So remember that in our main analysis, we're looking at the buffer zone. That's basically consumers located within 3 miles to the boundary of the true utility. We also relaxed that assumption and by changing the buffer length from 1 mile to 5 miles. And in all 3 study regions, our results are still stable across different buffer lengths, confirming our main conclusion. All right, and then we also look at the heterogeneity of the impact of rebate across different income groups. Here you can see that the income group that has the most positive response to the rebate is the income group between 50K to 60K annual income bracket. And you can see that for the consumers that have really high income, above 60K annual income, the rebate is no longer having statistically significant impact on them. This could be because even without rebate, these consumers can afford heat pump and plan to purchase heat pump anyway. So rebate itself does not induce additional installation. And then again, another interesting finding is that for the low income households with income below 20K or between 20K and 30K, the impact of rebate is smaller compared to households located in this income bracket. This could be because of liquidity constraint actually faced by these lower income households. And to recall that to qualify for a rebate, these households should actually first install the system first, meaning that they have to pay the cost out of pocket and then apply for the rebate. And then for these really low income households, if they have financial constraint or liquidity constraint, then the rebate is no longer applicable to them because they cannot qualify for the rebate because they cannot install the heat pump in the first place. Okay. All right, so to summarize, we know that the US government and government worldwide are planning to provide more funding for rebate and low interest programs to facilitate building electrification. And our study demonstrated that both policy tools can be effective at increasing the adoption probability. However, we showed that rebate program can be more effective, but the rebate program is less effective for the low income households. So we need other innovative policies and supports that's targeted at the low income communities. For example, there can be a combination of low interest loan program and rebate offered for low income communities instead of just having, for example, a single rebate or the low interest program for these communities. Okay. All right, so that's the first study, and that I mentioned earlier, this is work in progress. Your comments will be very helpful. All right, so next, let's move on to the second paper. It's a paper that we have already published at Nature Energy, where we're estimating the change in housing prices induced by heat pump adoption. And this is, again, joint work with my PhD student, Dr. Pengfei Liu from Rhode Island, my colleague Anand Patwardhan, as well as Dr. Parth Vernath from University of Michigan. Okay, so the motivation for the second paper is that if we can show heat pump installation can induce additional price premium for house transaction prices, then that can serve as another incentive for adoption. And this, again, goes back to the energy efficiency gap literature that I mentioned earlier, is that despite the fact that heat pump can generate some potential positive economic benefits, and despite the fact that there are various types of incentives existing for the installation, but then the adoption is still relatively slow. So in this paper, we're showing that there's another layer of the incentive that could potentially serve as a strong signal for the consumers to adopt this technology. All right, so again, we're utilizing the same data set. And then here you can see that we're forming the panel data set of heat pump adoption of individual houses. Okay, so here our empirical approach is, again, difference in difference in conjunction with the matching approach. So to conceptualize what this approach is doing we're building this graphical illustration here. Here, let's say that we have a control house. That's basically a house that did not adopt single heat pump in our study period. And then we also have a treated house. That's the house that adopted heat pump between 2 time periods. Now we know that even without heat pump adoption, there could be other factors that can influence the housing prices. And those are the baseline factors such as local economic conditions. And then we can eliminate the impact of these other conditions by, for example, looking at the change of the housing prices of this control house, basically S2 minus S1. And then that trend of the baseline control house price change can serve as the counterfactual trend of the housing prices. And then we can subtract these two differences to get a difference in difference estimation, and that's the causal impact of heat pump adoption on the housing prices. All right, so basically to qualify to be a treated house, it must be sold at least twice before and after the heat pump installation. And also to qualify for a control house, the house must be keep on using one specific heating technology other than heat pump. And also the house should be sold at least twice during the similar time window. And then the time span of our study is from 2000 to 2018. And also we conducted exact matching on counties, meaning that the control and the treatment houses should be located within the same county so that we're eliminating other regional factors. And also we're ruling out the influence of remodeling, because we all know that could be various type of factors such as building characteristics that can influence housing prices. So by ruling out the influence of remodeling, we're basically doing this by removing the houses that were remodeled after year 2000 from our sample. So lastly, in total, we obtained about 14,000 houses in the treatment group and 440 houses in the control group, covering 23 states across the nation. All right, again, our main empirical approach is the two-way fixed effects model. If you're interested in the detail of the model specification, we can discuss more during the Q&A session. Okay, so to further ensure you that we are indeed considering a comprehensive set of building characteristics, here these two figures shows you the set of building characteristics that are controlled for in our study. So as I mentioned earlier, by removing the buildings with remodeling after 2000, we basically can eliminate the confounding factors from changing building area, architectural style, swimming pool, parking space, and construction material. And then we'll also include two important control variables, which are building condition and building quality, that again can reflect the influence from this comprehensive set of building characteristics. Okay, so now let's look at our main empirical estimation results. Again, here I'm showing you 4 different model specifications with different control variables. You can see in all cases, the coefficient for heat pump adoption are positive and statistically significant. Now, based on this last model specification, it means that if if a house adopted a heat pump, then the historical transaction of the houses can increase by 7%. And considering the average housing values in the US, that 7% increase in price premium is equivalent to about $17,000 in additional transaction prices. And this estimation from the direct difference regression can be serve as the upper bound of the price premium. And the next, we also estimate the lower bound of the price premium by eliminating the potential confounding influence from the contemporaneous energy efficiency and building upgrades. These are the changes that could happen around the same time when building installed the heat pump. Now let's first look at the contemporaneous energy efficiency retrofits. We do this by using data from Residential Energy Consumption Survey, which is publicly available from EIA. We basically look at the correlation of heat pump adoption with the adoption of other energy efficiency technology and renewable energy technology. Here you can see that there is indeed positive correlation between heat pump adoption and the adoption of Energy Star qualified windows, water heating, light bulbs, refrigerator, and other appliances. But there is very low correlation between heat pump adoption and solar water heating and solar panel adoption. All right, now to eliminate any potential influence from these correlation of adoption, we basically web scrape the values of each of these building upgrades or energy efficiency upgrades from Home Depot. And then we combine those upgrades or multiply the value of those upgrades by the probability of co-adoption between heat pump and these individual upgrades. And then subtract the weighted value and the sum of these value together from the upper bound estimation. And then we can get a lower bound of the price premium. All right, similarly, we also need to consider other contemporaneous building retrofits. These are the changes in the building structure, such as changing of roof cover, improve our building quality, building condition, change of number of rooms, and number of stories. And then we basically find out these correlation from the Zillow data set. And then we conducted also a hedonic pricing by estimating basically price on each of these building features. And then we can get the value of each upgrades. And then we add those value together, weighted by the correlation of these building upgrade with heat pump adoption. And then subtract these value again from the upper bound, and then we can estimate the lower bound of a price premium, which is equal to 4%. And that is equivalent to about $10,400 in additional cash in transaction price. All right, and then next, we also look at the housing price premium by different other factors. So here you can see that there is indeed heterogeneity by these other factors. For example, the price premium is the highest for consumers with relatively high environmental awareness, for regions with relatively high heat pump density, for regions with mild temperature, and also for regions where the income is also relatively high. Okay. But here you can see that, interestingly, for regions that have very high environmental awareness and very high income, the price premium is actually not very high compared to these households located in the middle. This could be because, for example, for consumers that are really have high environmental awareness, they might actually know that in some regions, heat pump itself, based on the current electricity grid, can actually generate negative environmental impact. Okay. So this is because for regions that are still heavily reliant on fossil fuel generation, such as coal-fired power plants, then installing heat pump can actually generate additional emissions. Okay, and then also for consumers that are very high income, they might prefer other more expensive technologies, but more salient to their neighbors, so that they can showcase their environmental status. For example, in this case, they might prefer, for example, installing solar panels or purchasing a Tesla electric vehicles compared to installing heat pump, where you can only see the heat pump when, for example, you're actually located near the house or inside the house. Okay, so those are our hypotheses to explain the heterogeneity that we have observed in terms of the impact on heat pump. All right, so next we also compare the estimated price premium with the cost and benefit of installing heat pump. We're doing this comparison in Pacific and South Atlantic region. Here, the cost that we're considering is the cost of installing a heat pump. This is basically the price that you have to pay for the contractor to install a heat pump in the house. And the benefit that we have considered are the lifetime avoided environmental damage and also the lifetime fuel cost saving. Okay, so from this comparison, we can see that our estimated price premium, both the upper bound and lower bound price premium, are higher than the total net benefit, as well as higher than the cost of installing the air source heat pump. Okay, so you can see that this additional difference, you can see the difference between the price premium and the cost of the air source heat pump could be explained by transaction costs, information searching costs, and cognitive costs. So this is because, let's say that you're considering buying a house, and then if a house already has a heat pump installed, then you can save your efforts and time needed in order to install a heat pump yourself. For example, you have to go search for the appropriate contractor and compare different quotes, compare different technologies, and calculate the lifetime fuel cost savings, and also calculate cost benefit of this installation. And besides, you can also save your time of having to wait at home for the contractor to finish the installation project. So, and because of this transaction cost and the information searching costs and cognitive costs, and that's why you're actually willing to pay a higher price if a house already has a heat pump installed, than just installing the heat pump yourself. Okay. All right, so to summarize, in this study, we have shown that the heat pump installation can increase the house value, and which can serve as another strong incentive for consumers to adopt heat pump. Okay, and then this is important because a significant positive price premium can reduce consumers' risk of not being able to recover their investments when they sell their houses, when they move away. And then this is important because on average, based on the survey data, the average US households only stay within the same houses for about 7 years, and then they move on to another house. And then we show in our study that when they sell their house, if they have heat pump, that can increase their transaction prices. And then this finding is an important contribution to the literature on the energy efficiency gap. Okay, and the policymakers can use the information from our study on the potential price premium to influence consumers' choice, in addition to just providing the traditional energy labels. And on the traditional energy labels, which normally just show the benefits from fuel cost savings. But if somehow the policymakers can use our information and convey this information to the consumers, then that can serve as additional incentive for the adoption of heat pumps. Okay, so that's the second study. And then the third study, again, is a work in progress paper, so your comments and suggestions will be very helpful. In the third study, we're estimating, again, the impact on housing prices, but now we're looking at the impact of local urban natural gas leakage. And this is joint work with my PhD student and then Dr. Morgan Edwards, who used to be the postdoc in our school, and she's now at the University of Wisconsin. And again, Dr. Pengfei Liu from University of Rhode Island. All right, so to give you a little bit of background about gas leakage. So you probably know that some gas pipelines in the United States are over 100 years old and are leaking. To provide some quantitative evidence about severity of this gas leak problem, studies have shown that the combined yearly gas leak emissions of 6 US cities are larger than the gas leaks from the production process of the largest US natural gas producer, such as the Bakken Shale in the Dakotas. And then here in our study, we're focusing on Massachusetts. And by the end of 2018, the utilities in Massachusetts have reported more than 16,000 non-hazardous local urban gas leaks. And many of those local urban gas leaks have not been fixed for decades. So here, these two graphs shows you the distribution of those gas leakage. And then we got this data from a NGO called Home Energy Efficiency Team. Here you can see that these gray dots represent the repaired gas leakage, but then these orange dots represent the unrepaired gas leakage as of 2014 and 2018. So the key takeaway from these two graphs is that there can be a lot of unrepaired gas leaks in the urban area. And then those gas leaks can be problematic. First of all, we know that methane itself is 86 times more powerful as a greenhouse gas than is carbon dioxide over a 20-year period. Okay, and then in Massachusetts, the leaks from local natural gas pipes account for as much as 10% of the total city-level greenhouse gas emissions. So the emissions from those local natural gas leak is not trivial. It's 10% of the total Massachusetts greenhouse gas emissions. And then the gas leak can also cause other problems. For example, gas leaks can potentially cause explosions. We probably already all remember the 2014 Harlem gas explosions that caused fatal casualties in Massachusetts. And the methane can also kill the surrounding trees by suffocating them at their roots. And besides, the gas leak can also increase consumers' energy bills. And in addition, there are some recent studies showing that within the houses, the gas leakage can actually increase the risk of cancer. All right, and then there are also different natural gas leakage grades. The grade 1 leaks are the most hazardous and must be repaired immediately. And the grade 2 gas leaks are potentially hazardous and are only required to be repaired within 1 year. And the grade 3 leaks are temporarily non-hazardous and are not required to be repaired permanently. So you can see that for grade 2 and grade 3 leaks, they can exist in the local community for a long time. All right, these are just two headlines from the social media that you probably often see these days about local gas leaks. For example, this first picture showing the gas leak can cause fire, which can cause fear in local communities. And the second tweet shows that it can cause local traffic congestion. All right, and because of this increasing awareness of gas leaks, since 2014, the Massachusetts utilities have been required to report the gas leaks. And that's how we can get the data of individual gas leaks from this state. And then in 2016, Massachusetts also promulgated a law to require utilities to fix gas leaks with significant environmental impacts. However, despite the fact that this law exists, the fixing rate is still very low. Currently, only 60% of those gas leaks, only 40% have been fixed, and nearly 60% have not been fixed as of 2018. Then one main reason for this very low fixing rate is because of high repairing costs and the difficulties for the utilities to raise the fund to repair those gas leaks. And because of this difficulty, it is very important for social planners and policymakers to ask the question about whether repairing these urban gas leaks are welfare improving. And to do that, they need to compare the cost and the benefit of fixing the gas leaks. And that's where our study makes an important contribution by estimating impact of gas leaks on nearby housing prices, which can provide the benchmark for policymakers to evaluate the benefits of fixing the local gas leaks. Okay, and again, the data from this study comes from two NGOs, Home Energy Efficiency Team and the Gas Leak Allies. And then they report each individual gas leakage from 2014 to 2019. All right, and then again, the study design for this third study is also difference in difference. Here you can see, let's say that we have a gas leak represented by this yellow dots here. And then within 20 meters of this gas leak, there are 6 houses. In order to do a difference in difference analysis, a treated house should be sold at least twice. Once before the occurrence of this gas leak, and also at least once within the occurrence of the gas leaks, but before the gas leak was repaired. And then we select the control houses, are the houses that are located further from compared to these treatment house. They have to located 20 meters away, but within 500 meters away from this gas leak. Okay, and then these control houses should also be sold at least twice during the similar time window. All right, so finally, based on our selection criteria, these are the houses that in the control houses as represented by these red dots, and the black houses represented by these black dots. These are the treated houses, okay? And then we're doing the difference in difference analysis using these houses on this map. All right, so some descriptive statistics. In total, in Massachusetts, in our study sample, 61% of the reported gas leaks are within 20 meters of a house. And in our difference in difference analysis, there are 10 grade 1 gas leaks. Remember, these are the gas leaks that are hazardous and need to be repaired immediately, okay? But you can see that even if they are required to be repaired immediately, some of these grade 1 gas leaks are still not being repaired on time, so that a house transaction can even happen before a grade 1 gas leak are repaired. And in our difference in difference analysis, we have 129 grade 2 gas leaks and more than 1,000 grade 3 gas leaks. Okay, so here is our main results from the difference in difference analysis. When we look at all 3 grades together, the coefficient is negative and statistically significant. Here, based on the magnitude of this coefficient, it implies that if there's a gas leak happen, then that can reduce the housing transaction prices of houses within 20 meters away from the gas leak by about 2.6%. Okay, and then if we look at grade 2 and grade 3 separately, then you can see the impact of grade 2 is much higher. If there is a grade 2 gas leak, and without repairing the gas leak, it can reduce the nearby housing prices by about 11%. Okay, and this is because grade 2 gas leak are potentially hazardous and is more harmful than the grade 3 gas leaks. All right, again, we conducted some robustness check by changing the buffer zone. Recall that our current analysis is to select the treatment houses located within 20 meters. Okay, and then we changed that buffer zone from 25 meters to 200 meters. Okay, and the results are still relatively stable in confirming our main conclusion. All right, so now back to our policy question. So basically, social planners need to calculate compare the costs and benefits of repairing the urban gas leaks. From our study, we showed that a grade 2 and 3 gas leak can decrease one nearby housing prices by about 3%. That is equal to about 14,000 a reduction of transaction prices. And you can think of this number as the benefits of repairing the local gas leakage. And then we find the number of the repairing costs from utility report, which is that for average repair per gas leak, it is only about $3,000. So you can see the benefit of repairing average gas leak is higher than the cost of repairing. Okay, This implies that repairing the average gas leak in Massachusetts will be welfare improving. And as a result, the policymakers should fund and incentivize the repair of these gas leaks. Now, recall that we mentioned there can be difficulties of utilities to raise funds to do those repairs. But then because our studies show that there's negative impact on the housing prices, and that negative impact can actually serve as the willingness to pay of those homeowners to pay for the utilities to repair those gas leaks. And because of this positive willingness to pay, then policymakers or utilities could potentially increase the energy surcharge to the consumers and use the surcharge to fund the repairs. Okay. All right, and then this is still a work in progress. And then so next step, we plan to do some heterogeneity analysis of the impact of natural gas on housing prices, especially in the lower income communities and the ethnic minority communities. This way we can ensure that the social planners can adopt a more equitable way to repair the gas leaks across different communities. All right, so I think I've almost used up all my 40 minutes talk time. So that's the end of my talk. So thank you very much for your attention. And I look forward to your comments and suggestions. And also here's my email and my Twitter handles. And I look forward to stay connected.
Well, great. Thank you so much. That was fantastic talk. Amazing data sets, really interesting topics. We have a few questions have come in, but I was hoping to ask actually the first one, partly because of some firsthand experience recently looking to replace a furnace and an air conditioner in our house. And I'm wondering what you think about some of the complexities of imperfect information. So in our case, we were very interested in geothermal heat pumps. And so I'm wondering what you think about air source versus geothermal. It turns out in New Jersey, there's a 26% tax credit on geothermal heat pumps. We found in our case, it was still incredibly expensive. However, the air source heat pumps, what we found when we talked to a conventional HVAC company, they were very ignorant of them. They didn't work with them and they quoted us a price twice as high as a conventional system. We found another company that actually is quoting us a price lower than a conventional system. So we're going with them with an air source heat pump. So I'm just wondering if you have any insight onto how information could be better shared to encourage uptake of something that from a climate perspective is clearly advantageous compared to a conventional furnace and air conditioner, and which apparently can be cheaper at this point than a conventional system, since that's what our actual experience is with the company we're finally going with.
Yeah, so thanks, Denise, for that question. It's interesting to know that the price has dropped a lot for the air source heat pump since our study started, because at that time it was still relatively high compared to our conventional heating or cooling system. So I think you're absolutely right. There is information asymmetry of consumers. They do not know, for example, the actual cost. The cost has declined, so sometimes they just ignore the option when they start thinking about changing to a new system. So I think that's actually related to the fact that we're finding this difference between the cost of installing heat pump and the price premium. That's indeed, for example, you need to do a lot of information searching. You need to get quotes from different contractors and compare those costs. So I think that difference indeed shows that it takes time for consumers to actually know all the information needed. I think that's exactly where I think the government can intervene and reduce the cost of searching for those information by, for example, having more local marketing campaign, or for example, on the utility bill that receive, it can also provide more information of, for example, recent changes in the system of the cost and also those technology attributes.
That's a great suggestion. Thank you. Very interesting.
Also related to the geothermal heat pump. So after our paper was published, we get a lot of inquiries from practitioners, and there are actually a lot of geothermal heat pump companies. They wanted to know what's the price premium of geothermal heat pump, but unfortunately, we do not have the data for geothermal heat pump installation yet.
Yeah, ultimately, geothermal will be a better long-term climate response, but it seems like there's a lot of price variability there as well, because I mean, yeah, there's complexities there, which probably are beyond what we should spend time talking about right now. Professor Rob Sokolow had a related question, and I'll ask him to ask it himself directly, but it regards the choice between electric heat pumps and electric resistance heating, because his concern is that resistance heating is cheaper from a capital perspective to install, but uses more electricity. And so is there any evidence that people may be moving towards electric resistance heaters instead of air source heat pumps? But Rob, do you want to go ahead and ask that question? And Chuck, can you give him the ability to do that, please? here we go. Here he is. Good.
All right. Denise, you asked my question perfectly well. It seems to be neglected in conversations. In new construction, the resistive heating has always been the cheapest option. Electric resistive heating, which is like turning your house into a toaster with wires in the walls or in the floor or something. It's very wasteful, turning high quality energy directly into low quality energy without taking advantage of the thermodynamic benefit of a heat pump. In retrofits, I don't know, but does your database mean there's a rabbit hole here where you think you're subsidizing heat pumps and you're actually subsidizing resistive heating? Do you have any insights into that based on your database?
So based on our database, basically we do not have direct evidence about whether those rebates or incentives actually go into those traditional resistive heating system. But in our data, so we indeed have the information about whether a house has the traditional resistive heating versus actual heat pump. So, so basically in our paper, we're analyzing the impact on the heat pump, but we do not analyze the impact on the resistive heating. But in reality, as you mentioned, that it's possible that it could be that some of the incentive can go into this resistive heating that is also basically electrify the buildings. But we currently do not have those data yet. And also I want to show that in our environmental benefit analysis, we did consider, for example, relative to natural gas furnace versus relative to resistive heating, what will be the relative environmental benefits and costs in different regions. And then especially for example, in Florida, we do that comparison with the assumption that the majority of the traditional houses are using the resistive heating instead of natural gas furnace.
So I think the policymakers would benefit by having this potential flaw in policies identified early with data of the kind that you have access to.
Yes, that's a great suggestion. Thanks, Rob. Yeah.
Great, thanks. Professor Elke Weber has a question as well. Elke, do you want to go ahead and ask it yourself, please?
Can you guys hear me?
Yes.
Yeah. So my question is somewhat related to the previous two ones. When you look at the R-squared for heat pump adoption in your first study, it was relatively low, around 10 to 12%. And so I'm wondering what sort of insights you have about other factors that drive adoption, and related to sort of maybe other structural barriers. If you think about redoing an older house, is there any possibility if the house is heated with oil and water heated radiators rather than with natural gas and forced air radiation to still do a conversion?
Yes, so thanks, Sarka. That's a great observation that in our main panel regression that the R-squared is relatively low. That means that we're only explaining about 10% of the variation in heat pump adoption in our regression model. And that is because we're only focusing on the impact of, I think you're referring to the first study, right? The impact of, yes, the heat pump adoption, the impact of rebate and loan on adoption. And that is because we're only focusing on explaining the rebate and that in that regression model. And you're absolutely right that there could be other factors that can influence the adoption itself, such as building characteristics, for example, and also availability of local natural gas infrastructure that can also influence the adoption. And those factors are basically, we're eliminating them in our regression model, but not explicitly include those variables, but by using, for example, individual building fixed effects that can control for those local factors, such as building level characteristics, as well as local infrastructure change. But we do not explicitly model those individual factor because those factor will be eliminated from the difference in difference analysis, assuming that those factors do not change over time. So hopefully that answers your question, but I think that's an important question that we can do potentially in a future study by, for example, tease out those individual factors from the regression model and estimate the coefficient for those regression model. And currently we only show, for example, in one of our slides, the impact of individual consumer characteristics, such as income and their environmental awareness, as well as regional characteristics, such as cooling degree days, heating degree days, population density, and electricity price. But I think that's a great question that we can explore in the future.
Okay, thank you. We have about 2 minutes left. Is there anyone else who would like to ask a question? You could raise your hand now or type something if you have a question.
Oh yeah, so thanks for the comment about the gas explosion in New York, not in Massachusetts. Thanks.
So Colin Hickey raised his hand. If you would like to go ahead and ask your question, please do.
Yeah, can you hear me?
Yep.
Yes.
Okay, great. So I was just going to ask a quick question because you talked mostly about what policymakers could do, and I was curious if you had thoughts because of sort of working with Zillow and maybe also like realtors or realtor associations, like to broadcast or advertise or also use them as agents in the process of kind of like educating or getting any of this information across to consumers and not just on the policies, like the governmental policy side.
Yeah. Yes, I think that's a great idea. And this is related to Denise's question about information asymmetry. I think that's a good idea because these are the companies and then the real estate agents that have the most close contact with the potential buyers. I think you're absolutely right that in the future we can, for example, share our paper potentially with Zillow and other real estate companies so that they can convey this information to home buyers. Yeah, we have got a lot of interest from, I don't think we have got a lot of interest from the real estate agent, but most of the interests are from the installers and some energy efficient organizations and policymakers. But I think that's another entity we should target.
Yeah, I think that's a great idea. And Zillow actually has a precedent of working with scientists to look at how sea level rise might affect properties, coastal properties. And they actually did some adjustments on future property prices, projections based on, or even current property prices based on projected future sea level rise in coastal areas. So they may be quite interested. That's a great idea.
Yeah, thanks.
So good. This brings us to the end of our time. Thank you all for coming. And we look forward to seeing you next week. And thanks so much, Professor Q, for joining us. We really learned a lot and value your work.
Well, thank you. My pleasure. Thank you. Thank you for the comments. Okay. Bye.
Bye.